Okay, so yes, I'm Kyle, as mentioned before. At OpenPipe, what we do is we focus on training agents to be more reliable using reinforcement learning. We find that reliability is often the biggest bottleneck. I know that, actually, I'll do a show of hands. I know we asked this question earlier today. So who has deployed, who has at least prototyped an agent in your organization? Okay, basically everyone in the room, yeah. And I guess put your hands up again if you've had issues with like reliability with your agent. Okay, so almost the same. Yeah, it's almost yeah, like a full set overlap there. This is super common. This is in many cases, in most cases, the main limitation in getting an agent into production is actually getting those last 9 or 2 of reliability. And we're going to talk about how reinforcement learning can help you solve that problem in a very concrete way. Okay, so first of all, definitions. I've chatted with a lot of folks here in the morning with the great talks and sessions we've been having, and I think it'd be helpful to go over what we mean by reinforcement learning at a conceptual level. So what is reinforcement learning? What are we talking about here? I'll start with an analogy, which is reinforcement learning is like giving your agent on-the-job training, okay? So if you can think of if let's say you're using, say, O3 as your agent, basically O3 is incredibly smart and incredibly diligent at its job and everything, but it's never, every single time you call it in your agentic loop is basically new for it, right? It's getting like, it's like if you had a new employee on their first day and you gave them a nice big instruction manual and they read the whole thing, you're like, okay, go do your job, right? And maybe that employee could do a fantastic job, but they've never done it before. They don't know exactly what you're looking for, and so they might not always do it exactly the way you want. Okay, so what is reinforcement learning? It's when you take that same agent, and instead of just giving them the big instruction manual, you do that, and then you let them actually do the job a few times, right? You say, okay, let's say you're doing customer support. All right, take a call. Now I'm going to tell you, hey, this is what you did well, this is what you did poorly, and you do that a few times over. And of course, you'll see much better behavior. We see this with humans. All of us have probably felt that at a new job, and we see the exact same thing with these agents. So that's what we're doing here. We're basically, it's a way, reinforcement learning is a set of techniques that let you take that feedback of what is good, what is bad for your specific agent, for your specific use case, and use that to update the agent to do more of the good stuff and less of the bad stuff. So today we're going to be talking about how we actually do this. We are going to be using in service of that specific example, a case study. This is a project that we created at OpenPipe. It's called ART-E. Basically what it is, it's an agent that you can ask it a question in natural language. So you could say, what time is my flight on Friday, or how do I RSVP for, like my daughter's field trip or something like that. It will take your natural language question, it will go and it will run a bunch of searches against your email inbox and try and find the relevant emails to answer that question, read those emails, and then answer the question. So this is kind of our example agent. This is something, not this exact same thing, but this basic pattern of like, oh, natural language question, go use a bunch of tools to get the answer and come back is something we see come up a ton as we work with enterprise customers. I guess I should mention that as well. So quick plug for those of you in the audience that this might be relevant to. Our main thing at OpenPipe is we work with enterprise customers, typically Fortune 500 customers, to actually make all this happen and help them deploy agents successfully in production that actually solve their business needs. So anyway, happy to chat about that later as well for those that's relevant. But this is, as I was saying, this is a use case we see actually come up very frequently, where this general pattern of, oh, I need to be able to, search different resources, do sort of like a research or deep research task, and come back with an answer. So hopefully this is relevant to a lot of you. Okay, I'll give a quick overview of like how this agent works. So it's if you've built an agent, this likely is going to look very familiar to you. But basically, the thing is we have a few different tools, and the agent is using them to try and solve its problem. So, in this case, we have an example question. The user asks, hey, when is Sherry's move to Portland targeted for? We can see our agent's like, okay, I'm going to search our emails. I'll use the keyword Sherry in Portland. Makes sense. And then ask for 10 results. And so then our tool is going to come back and say, okay, here's a couple of different messages that have those keywords. And our tool is like going to say, oh, okay, or our agent is going to say, okay, yeah, it looks like this, this specific email that came back that starts with 182 seems relevant, so let's read that. It reads that into the context, and then finally at the very end it says, all right, yep, I've got enough information, I know how to answer this question, and it gives a final answer. This is the basic architecture of this simple agent that we're exploring. Okay, so how are we actually going to build this agent? First step, this is what we always recommend. We like working with customers that are already at this point, and if they're not, then we help them get to this point. You actually don't want to start with reinforcement learning, and I'll explain why. You want to start by building the agent the best you can using some prompted model. So that could be Claude through AWS, that could be O3, that could be really any model, whatever model does best on your task and works with your environment. There's 3 reasons I really recommend starting with this before you get into the reinforcement learning or training at all. The first one is, as you're in the case of this email agent, you want to make sure that like when it calls the read email function, it actually gets stuff from the inbox and like gets the results back. There's just a lot of debugging things that can get broken there, and it's a lot faster to debug if you're not also debugging your training loop at the same time. The second reason is you might not need reinforcement learning, right? Like if you can get good enough behavior from just a prompted off-the-shelf model and it meets all of your requirements, there's no need to do training and you can save a lot of time. And then the final reason, which in my opinion is the most important one, is because once you have those prompted baselines, so once you sort of know how good you can do on your prompted model and sort of the maximum performance you can reach after you've optimized those, then when you actually go and do reinforcement learning and you're able to exceed them, then you can just like gloat and like post on Twitter and like talk about how awesome it is that you trained this model. So that's my favorite part for sure. Okay. So this is what a good reinforcement learning run looks like, and I'm going to explain what we're looking at here. So this is for that task I was talking about earlier. This is the art e-task. We've got these sort of horizontal lines you see. Those show the performance of the different prompted models that we benchmarked. So you can see the highest performance one here is O3. And then O4 Mini does a little bit worse, still pretty good, and then Gemini 2.5 Pro and 4.1 each do a little bit worse. Okay, so those are sort of our baselines. And then you can see this blue line that's kind of like going up over time. That is the model that we're training. Okay, that's our we're using a Qwen 2.5 14 billion parameter model. That's quite a small model. And so you can see as you look at that graph, it starts out doing really poorly. So only about 0.4, so like 40% of the time right here at the very start, it's able to get the right answer, which is significantly worse than any of these. As we go through the training process and we're giving it that feedback and saying, hey, you did a good job, you did a bad job, you can see that it quickly learns, okay, this is probably, it's just like learning how to use its tools correctly, that gets it to a good spot. And then over time, it just gets more and more efficient until ultimately, after we've gone through like 500 cycles of this, by the end of this training run, you can see it's doing significantly better than any of our prompted models. This is sort of what you're hoping to see when you've got everything set up right. Okay, this is just another view in the exact same data we were looking at. I find this is helpful because it shows that even though in this view it looks like we're sort of plateauing out at a pretty similar level to those other models, if we look at the actual like final percentages here, we're able to get with our reinforcement learning approach to a 96% success rate in answering questions that the user asks versus our best prompted model is at 90%. And so if you think about it another way, it's like 60% of the questions that O3 is getting wrong, we're actually able to get right, which can make a huge difference in the user experience and just the level at which your users trust the agent to be able to do a good job. The higher accuracy that we're seeing here, the higher reliability, isn't actually the only benefit. There's a couple others as well that often come up in different contexts. First one is cost. So the model we're using here, as I was saying, is a relatively small model. It's a 14 billion parameter model, which is much smaller than O3 and likely O4 Mini as well. And so we're able to get much lower costs. And so from a unit economics point of view, you can see this is the cost per 1,000 runs. At that $11 or $7 per 1,000 runs, this may not be cost effective from a unit economics point of view for many use cases, depending on your pricing model. And if you can get that an order of magnitude lower, that can often make the difference between a successful and unsuccessful product. And then finally, this one actually comes up a lot and is often, the hard requirement even more so than cost, and sometimes even more so than accuracy or reliability, which is latency. And so for certain interaction patterns, you're gonna have a really bad. Your users are gonna really hate you if they're waiting many seconds to get an answer back. And so by moving to these smaller specialized models, because that model is smaller, it's able to generate responses faster, and we're able to get much lower latency. There's actually another reason why this latency is lower, which we're going to talk about later in the presentation. But we were able to train the model to take fewer rounds back and forth to the inbox to get a successful answer, and I'll talk about how we did that later on. Okay, so these are kind of this overview has been kind of explaining why you might want to do this, the benefits you're getting from doing that. Now let's talk about effectively the costs. Like what is the level of investment you need to make, because this can also obviously play into the decision of if and when to invest in this kind of technology. The good news is, so if I were giving a version of this talk about a year ago, which I actually did, I would say that you really have to wait a long time before this makes sense, because it was really hard. It's been getting much easier. The techniques are understood better. There's best practices that we're developing, and so the sort of barrier to entry there is coming down quite a lot, which is awesome. So for this run, it cost us about $80 in GPU time to train it. And then about 1 week of time from admittedly an expert in this area to make this project work. I actually think that time will continue coming down as well. But yeah, it's not a huge investment, which is pretty exciting for me. Okay, so all right, the next bit. This is going to be, I'm going to talk in the sort of like a little bit lower level. I'm not going to go all the way to to some of the other presentations we had this morning, but at a bit of a lower level, what the practical steps are, how you get this working. Hopefully this is helpful for those of you who want to go try this yourselves, and at least for those of you who are leading teams trying to make decisions, will help you understand what the concepts are and what you need to have in order to be successful here. All right, so there are, generally speaking, two big problems you have to solve if you want to successfully train a model with reinforcement learning. And there used to be more, actually, but the list is getting shorter as some of the other things are abstracted away and we get good techniques for them. The first one is you need a realistic environment, all right? You need to understand, you basically, the agent needs to be operating at training time in an environment that looks a lot like the environment it will be deployed at in production, because ultimately, if you're giving it feedback in a very unrealistic scenario, that feedback is not going to train it on what to do correctly. And the second thing is a reward function. So a reward function is it's basically just a fancy way of defining what good looks like, right? So when your agent runs, you need to have some way at the end of this agent's run to say, hey, you did a good job or you did a bad job, because that signal, if it was good or bad, is what you're going to be using to optimize against. So these are two things. Now, the reason I call these hard problems, they aren't always hard problems. In fact, the reward function is sometimes really easy if you're using verifiable rewards, which is a concept that was actually invented right here at the Allen Institute, which is awesome. But so they're not always hard, but they are things that you do have to think about very explicitly, and it's very task dependent which of these basically the right answers here. I'm going to talk through right now how we solved these two problems with ART-E, and hopefully that helps give an example of how you do it. Okay, first one of those, realistic environment. Okay, so for our email agent, right, this is an agent, as a reminder, that is taking a natural language query, it's going and searching an inbox, it's getting back at a final answer. So it needs an email inbox, right? It needs to be able to go search some inbox, and it needs to be able to try different techniques to do that and get the answer back. So, and that inbox, it should be large, because that's what a lot of real inbox boxes are. It should have diverse data, and it should be realistic. So this could be a hard problem, because sometimes users get annoyed if you're using all of their email inboxes. I don't know, like our OpenPipe employees didn't want me just training an email or an agent on all their personal emails. So this could be a hard problem. Luckily for this specific problem, we were able to rely on the contributions of an iconic company that has contributed actually a lot to the open data ecosystem, and especially to this email type of data set. I am, of course, talking about Enron, which from the laughter some of you probably have heard of. Enron was a large financialized energy trading company from the 90s and early 2000s. They ended up committing massive fraud and getting indicted for it and being completely killed as a company. But luckily for us, as part of the court process where they were shut down, they had to release the emails from all of their executives over an extended period of time. So we've got this great data set of 500,000 real emails from this company that we can use as our inbox. So yeah, we'll use that here. So now we've got our email inboxes. That's great. What's our second problem? We need a reward function. So when someone asks a question, hey, what is a good like they ask a question like what time is my flight on Friday or whatever, like I said earlier, and it gives an answer back. We need to know, is the answer right or not? We have to be able to say, did it do a good job or a bad job? And so there's different ways to solve this problem. The way that I chose to solve it in this case was by basically inverting the problem, okay? And what I mean by that is I started by, so I had these inboxes from the Enron email dump, and what I did is I took the email in, I went through the email inbox in chunks of like 20 emails at a time, and I took those 20 emails and I gave them to Gemini 2.5 Pro, and I said, hey, Gemini, here's 20 emails. From these 20 emails, can you please give me just a few questions that like a user might ask that the answer is in this email, and also tell me like what is the right answer from this email, okay? And then also tell me which of the email has that answer. And so, and it was a little bit more complicated than that. I had to do some post-processing to get the questions that actually looked realistic. But basically, that was the process. And so this is a way of generating synthetic data, which is very applicable to our domain. So basically, what I ended up with was a set of about 4,000 questions, and then answers, and then also the emails that contain those answers. And so once I have this data set, now defining my reward function becomes much easier, if you think about it, because I know what the right answer is to each of the questions. So now my reward function is really simple. I just give the question to my agent. I let my agent go out and search the inbox and everything. And then once it's done, it comes back with an answer. And since I know what the answer is supposed to be, because I generated it that way, I can just use a really simple like LLM as judge and say, okay, here's the answer that I got back from my inbox or from my agent. Here's the expected answer. Do these seem like the same answer? And I can use that. And if it is, I said, great, the agent did a good job. And if it's not, then I say, okay, you did a bad job. Let's improve. Okay, so that's basically it. So now we have our environment, we have these inboxes, we have our reward function, and we can actually train our agent. And really that's like, if you can define those two things for your task, the rest of it is pretty formulaic. It's pretty easy to do. So once you've got that done, then basically what you do is you just over and over and over in a loop, you take, in our case, those 4,000 questions, and we have our agent take one question, go all the way through, try and get an answer, decide, okay, is this right or wrong? Give it the reward, and you do that over and over and over again in a loop, and you reward it when it does good jobs, and you punish it when it does a bad job, and then eventually, if you set everything up right, it's going to work. And you get a nice graph like this, which we looked at earlier. So each of these steps is basically one iteration of having the agent try, I think, on like 12 different of those emails or 12 different of those questions to find the answer, and then basically just like do that over and over again. And as you can see, it actually gets better, which is awesome. Okay, this is a fun part that I think this is really cool and really powerful. Hopefully you agree as we talk about it. So one of the really cool things, in my opinion, about reinforcement learning is you get the ability to steer these models in a much more complex and subtle way, and optimizing for lots of different things if you want to, if you take advantage of it, more so than really you can get through prompting alone. And I'm going to talk about two of the ways we did that in this project. Okay, the first one. So you remember I mentioned earlier that we had lower latency because it was a smaller model, but also we had lower latency because we're actually taking fewer turns. And the way we achieved that was actually through, again, this reward function. And so what we did was we gave an extra, just a little, so the main thing we care about here is did it get the answer right? That's most important. If it gets the wrong answer, that's really bad. But if it got the answer right in two different runs, and in one of them, it used fewer turns, so it had fewer queries back and forth to the database of emails. We gave it a little bit of extra credit. We said, okay, yes, that's slightly better than the one where you got the answer right, and it took more. And you can see from this that it learned. So this is a graph of how many turns it takes to answer the question, how many times it goes back and forth to to read an email or list emails. And you can see early on, okay, it's starting low. Then quickly it learns, okay, I don't really know what I'm doing, so I just have to go back and forth a bunch to actually get an answer. But then as it starts figuring out what it's doing, it's like, okay, well now I know it's more efficient at knowing what the right search queries are, extracting the right information from each of those emails it reads. And so you can see over time it's learning to be able to use fewer turns back and forth. And by the end here, it's using significantly fewer turns on average than any of our prompted models, which again helps us with that latency and the cost, which is awesome. The second graph you see over there is it's a measure of hallucination. So when we ask our agent a question, there's 3 different things that could happen. It could come back with the right answer. It could come back and say, hey, I don't know what the answer is. I wasn't able to find the right email. Or it can come back and it can give a wrong answer, where it says, hey, the answer is X, and it was really Y. That last case is really bad, right? If it's making stuff up from your email inbox, that's much worse than just saying, I don't know. So what I did here is I gave it a little bit, actually not a little bit, quite a large extra penalty. So if it came back, so if our agent answered a question incorrectly, that was a much worse score than if it just said, I don't know. And so you can see from this last graph, we were able to successfully get the sort of hallucinated answers, which started really high, like 12% of the time. But as we trained, we got down to the point where it was hallucinating answers significantly less frequently than any of our prompted models. So that's one of the nice things about reinforcement learning is you can just throw a bunch of stuff into your reward function and optimize against all of those things at the same time. Okay, I'm going to go through this part really quickly. It's just kind of fun, honestly. So reward hacking. What is reward hacking? So one of the things you run into, and I think probably if those of you who've I don't know, been teachers or had children or probably had employees as well have probably run into this, where sometimes people who you tell someone what you want them to do, and technically they do it right, but it's not actually what you intended, right? They find some way to sort of game the system. Models do this too, all the time. So they try and find ways to get a reward without actually doing what you really want it to do. So this is a famous example here, where this boat is supposed to be going in a big circle around the track. That's what they were trying to train it to do. But it learned that there's these bonus points that just respawn here in the center, and it can just go in a circle there and just get the bonus points and get a super high score without ever completing the race that it's supposed to be doing. And so anyway, this is a fun example, but there's lots. This comes up a lot. So a couple of examples I'll give where this happens, and I'll talk about how you actually fix it, which is the real reason I'm bringing this up. So this is an example of a reward graph where you can see as we're going through our thing, okay, it's doing kind of poorly, boom, it does really great. Okay, you see this, is this good or is this bad? All right, well, in the context we're talking about right now, you're probably going to expect correctly that I'm going to say it's bad. So what happened here was, if any of you have played, I don't know if anyone's played the New York Times Connections game. It's this game, you get 16 words, and you're trying to put it in 4 groups of 4, and you have to there's lateral thinking involved in figuring out what the groups are. So we were trying to train a model to do that. It's it's kind of a hard task for especially these small models because it requires a lot of knowledge and also lateral thinking. And so it wasn't doing great for a while, and then all of a sudden it took off. And so we had there's an engineer. I don't know if he's here. There's an engineer on our team. Yeah, Anki back there. He sent this graph right here to our company Slack. He's like, hey, look at this. The model figured out NYT connections, getting almost a perfect score. And he was very excited about this. And then we were like, okay, awesome. Let's see how it did it. So we looked at the actual outputs. Unfortunately, what it had learned was that there was a slight flaw in the way we were grading this, and it could just put all 16 words in each of the 4 connections and get a perfect score. So it just completely ignored the purpose of it and figured out a way to hack around it. So another quick example. I was training an agent a few months ago to make posts for Hacker News. Hacker News is kind of like Reddit, and it's a forum where you can submit links and put posts. They get upvoted. So I was training an agent to try and come up with really good titles. So when you would submit these titles, it would be more likely to get upvoted. And so I trained an agent to, given the body of if you gave it an article, to try and come up with a title that could be submitted to Hacker News and get a lot of upvotes. Okay, so we're seeing great, first of all, really good behavior. This is actually a pretty good looking training run as well, where early on it's learning some stuff. You can see it's starting to get better. And then boom, we have this spike right here, right? Okay, so you can probably guess from the context of the talk, no, that spike does not mean that it just got fantastic at doing HN titles. What it came up with was it learned eventually that it could just completely ignore the content of the post and just gave the exact same title to every single post, which maximized the score. And the title it came up with was Google lays off 80% of workforce. And it just started giving that to every single HN, and it, the reward model was like, yes, that is great. That is for sure going to get upvoted on Hacker News, which is fair. It probably would be, but wasn't the purpose of the activity here. So let's talk about how you solve that. In my experience, this comes up a lot in most of the runs we do. This is a common thing that comes up with reinforcement learning. The key here is basically to treat it as an iterative process. So what you can do is if you start seeing a graph like this, what you should be doing is you should be saving all these traces to some kind of like observability platform or a database. It doesn't really matter where you save it, but somewhere where you can look at what the agent is actually doing. And when you see a spike like that, you go in and you actually look at what it's doing, right? And see if it's doing the right thing. And if it's not, then you figure out how do you change your reward function to stop it, whatever the thing it's doing. So in this case, both of these are pretty easy to fix once you see it. So the first one, we just edited the code to for that connections game, so it was correctly making sure there's only 4 in each group. The second one was actually also pretty easy. We just added an extra like LLM as judge to every single one of these, and it was just, hey, are the contents of the title actually supported by the article? And once we added that, it just fixed the problem. So it's usually pretty easy to fix, but in order to do so, you have to be actually looking at the model's behavior. Okay, promise I'm almost done. One last slide here. One final advantage of doing this training and moving to these smaller models is that it gives you much more deployment flexibility. And that's one of the things that I'm really excited we're here with AWS because we have these small models, our customers are able to deploy across many different environments, and they have much more flexibility. So you can still, there's lots of services out there that'll still do serverless hosting in the same way you would call OpenAI or Anthropic or Gemini or any of those. So you have that option still. But you also have, once you've trained this model for yourself, you have the option to deploy on-premise. And of course, you have the option to deploy on services like AWS Bedrock. We have a direct integration with AWS. As we train models for our customers, we can deploy it directly to Bedrock. And that's been, that flexibility has been super useful for them. Yeah. Found the AWS guy. Okay, I'm going to skip these because it's basically, well, anyway, this is just rehashing what we saw at the beginning. With reinforcement learning, you can get to a better place. Someone, I don't remember which speaker, one of the speakers this morning mentioned the Pareto frontier between cost, latency, and reliability. Reinforcement learning expands that Pareto frontier significantly, so you have the option to get to a place that's better on those. You still have trade-offs, but you have better trade-offs available to you than you have with just prompting alone. Okay, couple of different links I'm going to share for those of you who want. The first is I did a big write-up of this project with more detail than we even got to in the talk. So if you're interested in learning more and want to do this for yourself, you can definitely get that or just look for Art E OpenPipe. And then also for those of the practitioners in the room, those who want to do this for yourselves, we have a Discord where we talk about reinforcement learning stuff. We share the projects we're working on. It's a great place. So if you're doing this for yourself, if you're interested in learning this technique, it's a great place to go and chat with our team and lots of other people thinking about this. So yeah, that is everything for me. Thanks everyone.